My name is Ryan Hulguin. I'm an HPC applications engineer with ARM. I provide support and training for the ARM tools, considering of ARM Forge, which is our debugger and profiler, and also the ARM compilers for the ARM hardware. For today's talk, I'll be going over, I'll start off with general debugging and profiling advice, and then I'll go into specific solutions that ARM offers for you to debug and profile your applications. And then I'll close off with a few slides on theta-specific settings that you need to be aware of using our tools on Argonne's machine theta. So the idea of debugging, it's really just about transforming a broken code and turning it into a working one. So what you see here is a nice little acronym of things to remember if you ever encounter a broken code, and these are kind of things that you can think of as you're trying to fix the problem. One big thing that we kind of we want to emphasize is tracking your problem. So if you have an issue, it's always a good idea to make a note of, to write it down somewhere, whether it's in a Word document or like a handwritten notes. Just track it, because a lot of the times the problems that you run into, you're going to see again. And the last thing you want to do is run into the same problem and forget how you fixed it last time. So it's always a good idea to write it down. So along those lines of recording your work is also find a way to reproduce the problem. You might start off with a large code with a large problem, and it has a bug that you've encountered. Ideally, you'd like to minimize the problem. So try to shrink it down to as small of a size that you can handle. Preferably if it's a parallel application, see if you can reproduce the issue serially. If you can't, try to limit the number of MPI ranks or threads that you're using. Yeah, so those are just some techniques of just general debugging principles. And once you've worked out the bugs in your code, the next thing you might want to focus on is profiling. You want to make sure that you get the optimal use of the hardware that you're running on, and try to run it as fast as possible. So what you see here is kind of a flow chart of things that you might be interested in looking at. So for instance, for the file I/O, you might want to focus on like the buffers, the data formats, and the in-memory file systems. Notice that I have CPU listed on the bottom here, focusing on vectorization. It's not to say that vectorization isn't important. What this flowchart is trying to represent is that if you have, say, a communication issue where you've got an MPI load imbalance and some MPI ranks are waiting for other MPI ranks to finish, it doesn't matter if your code is vectorized, because it's going to have a big slowdown if you have some type of MPI load imbalance. But all of them are important, and it's a good idea to use a tool, whether it's our tool or doing your own timings, to get information about your code. Really understand where time is being spent in your code. So just a general workflow. If you've got an application, you want to do your profiling on not some dummy test case, but something that's realistic, something that represents that you would do on a normal production run. At that point, once you have a realistic test case, just run it through a tool, profile your code, and then look for the significant. It's which part or phase of the code is dominating the time, and try to see if there's anything that looks unusual to you. So a lot of times you don't realize that you're spending more time in a section until you actually do some profiling. And then once you figure that out, try to ask yourself, why am I spending all my time here? Shouldn't the code be spending its time elsewhere? And then also, think of the future. Just because it profiled well on your current hardware for your current run, try to ask yourself, what happens if I increase the number of MPI ranks, or if I increase the number of threads? Try to predict just how well it scales, or even do scaling studies. So that's just some general information. At ARM, we have some commercial software available, namely in our product that we call ARM Forge. Forge consists of both DDT, our debugger, and map, our profiler. While you're here, I would highly encourage you to use these tools, mostly because they are commercial, and then you'll have access to use them for free here during your time here. And you can often find them on some of the world's largest supercomputers. It's not only for x86, we also have it on ARM, of course, and IBM Power, and it also works with NVIDIA GPUs if you're into that kind of programming. It's fully scalable, whether you're just doing some local work on your laptop or you're using hundreds of thousands of cores. Our tools are designed to work the exact same way so that you don't have to learn anything new if you're moving to one system to another. And hopefully from the demonstrations that I'll show you in a few minutes that you'll see that it's very easy to use, it's very intuitive. A lot of times you can just get information just by hovering your mouse over certain areas. And that's pretty powerful to get the sort of information you're looking for very quickly. So specifically, we have DDT, which is our debugger. And it can be run in two different modes. You can run interactively with the graphical user interface that you see on the right. Or also we have what's called offline mode. So where you don't have to be babysitting your computer if you know there's a bug and you want to run it through our debugger. So essentially, you just take your command, for instance, on Theta, you would use ap run, the number of ranks and the executable, and just stick DDT -- offline in front of it. And if you do that, so as soon as it actually runs, so this will be something you would put in your submission script, where you would just prepend DDT -- offline in front of it. And when it actually runs, it'll generate this nice, beautiful HTML output. And anytime there's like either a manual breakpoint that you specify, or if there's a crash in your code, DDT will take an instantaneous snapshot of that moment and show you like the local variables and the stack backtraces and things of that nature, so that you can refer to it at a later time when you have a chance. Okay. All right, on the other side of our tool, we have map, which is our visual profiler. So the idea is to be able to see at a glance where all your time is being spent. So for this picture here, you can see it's showing you from left to right, where left is the start of your program and right is when your program finishes. And then the color-coded, it's color-coded nicely so that you can see if there's a lot of green, that means you're doing a lot of computation. Green is typically good. Blue it is representative of communication. And if you notice that there's a lot of communication more than you expected, there might be a problem in your code. And also, you can also see in the time here, it'll show you the source code and also the percentage of time spent at lines in various source code. Okay. All right, so focusing more specifically on DDT. So you would use our debugger, once you've identified that you've got a problem. So the idea is to use the tool to gather information about what happened in your code. So these are the types of questions that you typically want to gather, like who, where, how, and why. Like who had a rogue behavior, where did it happen, how did it happen, why did it happen. At the bottom right, you can see a little section that DDT will show you. You see the stack backtraces, and it's actually telling you that there are 150,120 MPI ranks. And of those, all but one are at line 300 of communicate.f90, and one rank is at actually line 303. So this is kind of helpful if you've got some type of a deadlock. So if you pause your application in DDT, it'll show you exactly where each of the specific ranks are and what line of code they're executing. Okay, so that's the usefulness of the stack backtrace. And also, you can see the path in which which functions were called in order to get to the current line of code that they are currently at. And above it, what you see are two variables, jcall and mype, and to the right of it, you have numerical values. So the numerical value is specific to the current MPI rank that you're looking at. And to the left of it is what we have, or what are called sparklines. So that's a graphical representation of the value of this variable across all of the MPI ranks. So for this particular example, this was actually a pre-production MPI library, and myPE was supposed to correspond to your MPI rank. And you should all be familiar with myRank by now, and it's supposed to be linear value from 0 to the number of ranks minus 1. So quickly, they were able to see from the sparkline, that this was not the case, and that they've got a bug in their code, and they were able to fix it for the production MPI library. Okay, so that's talking about the tool. So how do you use it with your own code? So it's fairly simple. What you want to do is you want to take your code and you want to recompile it with -G so you got the debug flags, debug symbols available. We also recommend that you turn off debugging options with -O0. If you fail to do so, or you just forget to, sometimes the compiler actually optimizes out some variables and some functions, and if that's what you're interested in, you might not be able to gain the information. Okay. So this is a typical use case with DDT. You've got some type of seg fault, you run it, and it crashes. Okay, so we got a problem, so let's run it with DDT. It's fairly intuitive. When you run under DDT and you just hit play, it'll actually stop at the line of code where the crash occurs. And it will not only stop, it will give you some extra information that will help you figure out what's wrong with the code. For this particular example, we've got a segmentation fault, and the reason is we're trying to access memory that's not mapped to an object. In particular, we see that we're trying to access this array called tab, and we're trying to access indices x and y, where x is some really large number and y is 0. Okay. So as I said earlier, if you hover over tab within DDT, you get some really useful information. So DDT tells us that tab is an integer array, with 13 elements, 0 to 12. And clearly, we're trying to access something that's outside of these bounds when x is like 4 million, something. Yeah. Okay, so that should be enough information to help you figure out, hey, what's wrong with this code? This is why we're crashing. Okay. So this is a crash that was pretty blatant and explicit, and you know it doesn't work. Sometimes you'll have other bugs in your code where it'll work sometimes, and then other times it just magically doesn't. Imagine that. So usually this is a sign that you've got some type of memory issue. At this stage in the game, if you can't reliably reproduce it, it's time to start debugging your application with some memory debugging libraries to track the source of this problem. And the way to do that within DDT is when you launch it with DDT in the run dialog, you just tick this checkbox, memory debugging, and then from there you're presented with all these memory debugging options. So under heap debugging, you see a little slider. By default, it's set on balanced, but you can either put it to left to fast or right to thorough. So as this slider goes either left or right, what it does is it enables more checks on your code. We link against our memory debugging libraries, and depending on the slider, you can have different types of checks on your code that will happen automatically for you. Do keep in mind, though, that the more checks that you apply to your code, the more overhead it's going to incur, both in terms of the amount of memory used and the amount of time it takes to run, because it has to do all these checks for every memory allocation. So in addition to the heap memory debugging options, we also have something that's called guard pages, which is underneath in the second section. You just check that, tick that checkbox to add guard pages either to the left or to the right. And guard pages are these little safety measures, sometimes also known as electric fences. And the idea is it protects your memory allocations. And if you access something beyond the memory that you allocated, DDT will prompt you and say, hey, you're not supposed to be touching this part of the memory. Okay. But do keep in mind that this is a fairly expensive thing in terms of memory usage. So if your application is already using a lot of memory, I would suggest that you either run a smaller problem case or allocate more nodes so that the number of memory available per MPI rank is greater before you turn this on. Okay. So one of the biggest competitor to our debugger is not other tools, but actually just using the print statement. I'm sure a lot of you are already comfortable with using print statements to debug your code. But the problem with that is that it's not a scalable solution. If you go across like tens of thousands of MPI ranks, that's a lot of data to sift through. So on this slide is an example where we had a code. It used over 17,000 MPI ranks, and this problem didn't show up at lower ranks. So they ran it through DDT to figure out, hey, why is this program crashing? And it turns out that they identified that it was crashing in this libpar metis library, in particular at this line, where all it's doing is it's taking the value of one array and assigning it to a value in a different array. Nothing strange here. But when they went to look further into this issue, so they decided to look at, say, what is the value of NT samples? Well, they forgot to turn off the optimization flags. So this is what happens if you leave the optimization flags on. So the compiler is so smart, it doesn't think it needs this variable, so the value is optimized out. So when you're trying to debug it, you don't know what that value actually is. So they had to go back, recompile their code with -O0, and then try it again. All right, so once they've done that, they now see that NT samples now has this value of like what, 1,800,000 something. Okay, again, everything looks fine. So based on what you see here, does anyone have an idea as to why this code is crashing? Okay, so those are the values, and this is kind of what we're evaluating, I times NT samples, divided by the number of processes. Everything looks fine, right? No problems. I'm sorry?
Out-of-bound is outside of the random, right?
Not quite. No. So yeah, those are valid numbers. So what's happening is I is being multiplied by NT samples. And when you do that, you actually get a negative number. How is that possible? Like we started with two positive numbers, and then when you multiply it, we got a negative number. Well, I'm sorry, say it. Yes, this is an integer overflow. Okay, so anybody have an idea on how to fix this problem? Okay, very good. Okay. All right, yeah, so So this was a real use case where someone used our tool to figure out, hey, something crazy is going on. All right. Okay. Yeah. All right. Okay. So, all right, moving on to a different feature with DDT. So DDT supports version control. Hopefully, everyone in here is using some type of version control to keep track of changes in their software. So a lot of times, if you have a new bug in a code that's being version controlled, typically the new bugs come from the latest changes. So it's nice to show that to look at the code that was just newly modified to track down any new bugs. Okay. So I'd also mentioned the tracking your work. So as programmers, we like to think that we can solve bugs in a matter of hours. But in reality, sometimes it takes longer than that. It may take days, weeks, or months. And if you're in that type of situation, DDT has a helpful feature called the Logbook. So where it tracks every single command that you've sent to DDT as you move through the source code. Also, it also shows you like the current stacks, the local variables, and so on and so forth. You can also add your own annotations with that pencil. Just click on the pencil, put your own notes, and then save it as an HTML file to review later. You don't have to do it, but this is kind of a nice, useful feature. Okay, any questions so far before I go into a real live demonstration? No? Okay.
I do have a question.
Yes?
Is the logbook stored for user?
Yes, it will be in your home directory or wherever you decide to save it. Yeah. And it's only seen by you. Yeah. Okay, so at this moment, I'll switch on over to my terminal. Hopefully I got, oh no, I lost my, I lost my connection. Sorry, it's going to take a minute to recover here. While I'm waiting for that to come back, let me just go through a few more slides. So these are some things that you can do with DDT. As I said, DDT is a nice scalable alternative to just print statements. With the Spark clients, you can see the value of variables across all of the MPI ranks. You can trigger what's called a watch point. So if you're interested in a variable and you have a suspicion that its value is being changed, even though you don't recall explicitly changing it, you can set a watch point on it. So what that will do is DDT will alert you anytime there is a change made to that variable. Additionally, we have static analysis warnings. So for instance, if you have an array that you allocate, you put some variables in it, you put some values in it, but you don't ever use it, and you meant to, DDT will actually show you that kind of information on the side. And also, we've got our memory debugging tools to show you if you access things out of bounds or if you have a memory leak or some stale memory allocations. So how would you use this on Theta? So you would have to, so I am requesting an interactive session, but you can also do it through a submission script just by modifying your script. So you would want to load the Forge module, and you have to explicitly ask for 19.1.2. If you just say module load Forge, you're going to get an older version, I think version 6 or something like that. I'm also going to recommend that you also unload the exalt. If you don't unload that module, I mean, you'll just see some kind of error message about qstat permission denied. It won't harm your code. You don't have to do it, but it's just something. If you're wondering why you see that type of error on Theta. Okay. All right. So that's how to run the code. I'm still waiting for a job. Okay, so I've got an interactive session. Just going to quickly go to the @pest demonstrations that I have available. Okay. So this particular example, if I run with 4 MPI ranks, it should run fine. Yeah. And if I ask for 8, it's going to crash. Right? Now it's... oh, no. Oh, because I have to recompile it, that's why. Sorry, just a second here. Wait a minute. Oh, that's because I broke it. Sorry, I fixed it. And I took out the bug. All right, let me recompile it so it's still bugging. Hey, there's our segmentation fault. Okay. So you want to run this with DDT. You know there's an issue, so you just take your natural command that you have and stick DDT -- connect in front of it. So what this will do is this will connect back to my local machine. So in another terminal, I've already started up Forge, and I've already connected to Theta with these configuration options shown here. This will be in the PowerPoint slides, so you don't have to worry about that right now, but this is how you would configure your client. I'm already connected, so all I have to do is just say DDT -- connect. Oh, I have to load the module. Forge 19.1.2. Doing 10 times. Okay. All right, so this is now asking, do I want, yeah?
So where are these codes available in the directory?
I'm sorry?
Where are these codes in the directory? The codes that you have, where can I find them?
Okay, they're not available at the moment, but before the hands-on period, I'll make them available to you. Yeah, yeah, yeah. Yeah, so what I did was I just established a reverse connection. So essentially, the machine on Theta is connected to my local, is trying to establish a connection to my local client here. Okay. So this is what I was saying before the QStat permission denied, and that's just because the exalt module is loaded. You can ignore that. Oh, I forgot to turn on. I must have memory debugging check turned on, but we're not using it for this code. So, okay, so by default, DDT will break in either main or MPI init. In this case, it was MPI init, and because the Darshan module was loaded, we were in the wrapped version of MPI init. But we don't need to worry about that. All we worry about is our code, hit play to get to our crash, and then you can notice that processes 4, 6, and 7 all crashed. So notice that they're now red. The other MPI ranks are actually still running, denoted by the green. And we can just pause them all, and then we can see that they're all in different places by looking at the stacks view. So we got 3 ranks at line 109, 1 rank in 151, and then 4 ranks in 168. But so again, we've got this tables array. This is a C version of what I showed earlier, and then we're accessing X and Y, where Y is the large value, and tables is clearly a float with 12 elements by 12 elements. Okay, so I'm just going to quickly fix this in here. So it should have been a for loop rather than a while loop, and then we don't need this manual plus equals rank. So I can modify the code within DDT. I can save the source file. Okay. And then actually, I'm going to end the session. All right, so then now that I know that I've fixed it again, so now I'll recompile it and then run it again with DDT. 6 minutes. All right, so we don't want memory debugging turned on, so I'm just going to uncheck that. Okay, so I fixed it. I just changed the while loop into a for loop, and then after I fill in that array, what I'm going to do is I'm going to set a breakpoint right after that for loop. I just right-click in the left side here to say add breakpoint for all. And then when I hit play, everything should now run to that breakpoint. Okay, and then pause. And at this point, what I can do is I can actually view the values of this array by just right-clicking tables within the GUI and say View Array and evaluate. So this is the numerical representation of that array for rank 0. If I was interested in the values of, say, rank 4, all I have to do is just switch on over to rank 4 and then reevaluate, and notice that the values do change. If I were interested in, say, the first row of the array, I would just change this $I to 0, saying I just want the first row. And then if I wanted to see what these values are across all the different processes, I can increase the distributed array to 1. And so notice now that I have processes 0 through 7 corresponding to my MPI ranks. And so this is now showing me the numerical value of the first row of this array for all of the MPI ranks. Additionally, I can click Visualize, and I can see it in a visual manner. And if I wanted to, I can save this as a PNG or something like that. Okay. Any questions so far on DDT? Okay. So in the interest of time, I'm going to go back to my presentation. Let me go back to expand. Keep settings. All right, so that was DDT, and then I'm going to quickly go over Map or Profiler. So essentially, it's a nice little tool to generate information about your code, figure out where time is being spent. So these are the kind of things that you can see at a glance. You can quickly see if there's any type of memory leak in one or all of the MPI ranks over time. You can see if there's an MPI load imbalance. Typically, if you have a sawtooth pattern, that means one MPI rank is waiting for another MPI rank before it can finish and move on and do its thing. You can see how well the vectorization is shown in different points of the code. Like I said, left to right is left is when your program starts, and right is when your program ends. So this summer, I had an ARM intern, and I tasked him with creating a 2D Laplace solver. I'm sure some of you are already familiar with that algorithm. And he coded it up, and what he did wasn't wrong. So, so he was tracking the largest change, so he's computing new values based on the surrounding neighbors, and then he's computing the difference between the new value and the old value, and he's tracking the largest changes. And he's got this statement here. It's, if you're not familiar with the syntax, it basically boils down to an if-then. If diff is greater than max diff, then we have a new max diff. Otherwise, it's the same value. And there's nothing conceptually wrong. It runs, it gets the right solution. But what I was trying to show him is that there's actually a performance penalty for doing it this way. So it started off running for 48 seconds. But what I did was I commented out the conditional where he's tracking the max diff, and I just ran for the same number of iterations that the previous profile ran for, and it runs 20% faster. And also, if you look on the right, the operation for line 203, it's now vectorized, whereas before it was scalar floating point. So scalar floating point, now vector floating point. So this is a key point in HPC. If you want to kill performance, put a conditional in your innermost loop. So does anybody have an idea how to properly fix this while still tracking the max difference between iterations? No? OK. So I'll just go ahead and cite. So one thing that you can do is instead of computing the difference here, is actually you store an array of differences. And then you compute the largest one in an outer loop rather than having it in your innermost loop. So that's kind of like a key point in HPC. Sometimes you have to sacrifice memory for performance. OK, so this is also map on another code, Cloverleaf. We were just showing that the I/O is really slow. Basically, it's got 14 megabytes per second. But when you use HDF5, which is a nice high-performance HPC library, you start getting well over 73.5 megabytes per second. And that just that little simple change of using a different input-output library allowed this particular application to run faster. In addition to just profiling normal code, we also have Python profiling. So in the interest of time, I'm just going to show you that it does work. You just take map-profile on your Python. So this is the naive implementation with Python, just normal Python. And then if you use the NumPy array notation, you get much better use of the CPU units. OK, and then again, these are a cheat sheet of how to use map on your code and a couple things that map can do. And if you wanted to do this yourself, like I said, I will make these codes available for you. And just one thing to remember on Theta, you have to use, if you're doing memory debugging, you have to link against our libraries. And if you're doing profiling, you have to build static profile libraries. But the instructions are here. OK, any questions? No? OK. All right, thank you.